The result I of the preceding problem suggests an immediate generalization. Thus consider the expression sum over R and S, PRPS, UR to M, US to M, UR minus US squared, where M is any integer. When M is even, this expression can never be negative. When M is odd, it can never be negative if the possible values of U are all non-negative or all non-positive. By performing the indicated multiplications in I, show the following results. U to the n square average is less or equal to the U to the n plus 1 average, U to the n minus 1 average, where n is n plus 1, defined as n plus 1. If n is odd, this inequality is always valid. If n is even, it is valid if the possible values of u are all non-negative or all non-positive. The equal sign applies only in the case where a single possible value of u occurs with non-zero probability. Show that this implies, as a special case, the inequality 1 over u average is greater or equal to 1 over u average. 1 over the average value of u. Valid whenever the possible values of u are all positive or all negative. The equal sign applies in the special case where only one value of u occurs with non-zero probability. Okay, so we're going to start out with this expression. Let's say consider the expression. This is given in I. Where we have sum over R, sum over S, all possible values of R and S, PR, PS, U sub R to the M, U sub S to the M, U sub R minus U sub S square. So the problem statement basically goes through the cases when this is going to be positive, so it can never be negative. So when is this expression greater or equal to 0? So we have a square here, so UR minus US square, so that's always going to be greater or equal to 0. Then we have probabilities. Probabilities can be 0 or can be positive values. It's a value between 0 and 1. So we need to have UR to M, US to M greater or equal to 0. So if I have an even number for M, for even M, what will happen? For example, M equals 2, then I would have UR square and US square multiplied with UR minus US square, which is always going to be greater or equal to 0. So this is true for even M. And for odd M, if M is an odd number, then I want the product to be greater or equal to 0. The product of two numbers is going to be greater or equal to 0 if they have the same sign. So this is going to be true for all u are greater or equal to 0, or all u are should be less or equal to 0. So basically the statement that the possible values of u are all non-negative or all non-positive. So all u values non-negative or non-positive, which means they are all positive or they're all negative. Then this inequality will hold. Okay, So, for example, if you have minus 1 to the power 3 and minus 3 to the power 3, you would have 27 times minus 1, which would give you plus. So both of them are negative, or both of them are positive. It's positive anyway. Okay, so I'm going to expand this square term here. So basically I can say that this is sum over R and S, PR, PS, UR to M, US to M, and here I will have UR square minus 2UR US plus US square, and this is greater or equal to 0 under these conditions. And this is equal to sum over R and S. So now I'm distributing this over the second term, the square term, PR, PS, UR to the power m plus 2, US to the power m, minus 2 sum over R and S, PR, PS, UR to the power m plus 1, US to the power m plus 1, and then plus sum over R and S, PR, PS, UR to the power m, US to the power m plus 2, and this is greater or equal to 0. Now I can basically look at this expression and I can see that this is the product of two things, two summations, sum over R, PR, UR to m plus 2, that is multiplied with sum over S, PS, US to the power m. And here I have minus 2 sum over R, PR, UR to m plus 1 multiplied with sum over R, sum over S, PS, US to the power m plus 1, and then the last term I have sum over R, PR, UR to the power m multiplied with sum over S, PS, US to the power m plus 2, and this is greater or equal to 0. Now I recognize that if I have UR to m plus 2 multiplied with the corresponding probabilities and summed over all possible R values, basically I'm looking at the average value U to the m plus 2 average value. And here I see summation over S, PS, US to the power m. That would be the mean value U to the power m mean value. And then I have minus 2. Similarly, now it's the same thing for UR to m plus 1. So this would be U to the power m plus 1 mean value, and then summed over SR or S doesn't matter. It's again U to the m plus 1 mean value because we're going over all possibilities. And the last term is sum over R, PR, UR to m. That is U to the m mean value, and then we have the last term sum over S, PS, US to the m plus 2, so U to the m plus 2 mean value, and this is greater or equal to 0 under these conditions. Now you can see that the first term here, I can see that it's the same thing as the last term here. So basically I would have twice u to the m plus 2 mean value, u to the m mean value, minus twice u to the m plus 1 mean value, and this is squared. This is greater or equal to 0, so the 2's will disappear, and I will find that u to the m plus 2 mean value times u to the m mean value is greater or equal to u to the m plus 1 mean value squared. Now, in the problem statement, we define n as m plus 1. So, if n is equal to m plus 1, then for m I substitute n minus 1. So with this substitution, my result becomes u to the power m plus 1 mean value, and this is u to the power n minus 1 mean value is greater or equal to u to the n mean value squared. So let me check what I was supposed to show. U to the n mean value squared should be less or equal to u to the n plus 1 mean value times u to the n minus 1 mean value. So just to make sure here, so it says u to the n squared mean value. Let me check if I have made a mistake here. So the term I get was u to the n plus 1 mean value twice. So that came from this part, and you can see that u to the n plus 1 mean value, then we take the square. So what I have obtained is correct. So this bar actually is belonging to u to the power n, rather than it's u to the n squared mean value. So this should be written as u to the n mean value squared, rather than u to the n squared mean value. So you can see that's what we have obtained here. Okay, so that's basically the result for part A. So we have gone through this expression and we have shown that this is the case. Now the problem says this is going to hold if n is odd. So if m is even, so you can see the condition was given as for even m. So if m is even, we have n is odd. So this is true for odd n. And if m is odd, we have n is even. So if n is even, for even n, it will hold for all u values non-negative or non-positive. So basically I have translated this statement here and basically checked what happens if n is equal to n plus 1. So what I obtain is that the inequality is correct for all for even n values. This means it's correct for odd n values, and it is correct for even n values when the u values are all positive or all negative. Okay. And when do I have an equality? So going back to the expression I started out with, sum over rs pr ps ur to the power m us to the power m, then I had ur minus us squared, this is greater or equal to 0. When is this equal to 0? This implies if PR or PS are non-zero, then I must have UR is equal to US for all R and S. So that means there is only one value, so as stated in the problem statement, a single possible value of U occurs with non-zero probability. So going to the end of this derivation, where we have found U to the n plus 1 mean value and U to the n minus 1 mean value is going to be equal to U to the n mean value squared if there is only one U value with non-zero probability. So as stated in the problem. Now going to part B of the problem. Part B is about 1 over U mean value. So when do I obtain 1 over U mean value? So if you have, if n is equal to 0, you can see that, which is an even value for n, then I would have U to the 0 plus 1 mean value multiplied by U to the 0 minus 1 mean value is greater or equal to U to the 0 mean value square. So that means I have the mean value of U multiplied with the mean value of 1 over U is greater or equal to 1. So this implies that the mean value of 1 over U is greater or equal to 1 over the mean value of U. And this happens for n equals 0, which is even. So remember that if n is even, m is odd, we must have all U values, for all U values, non-negative or non-positive, which means they're all positive or they're all negative. So we have shown that this is the case as suggested by the problem statement. Now the equal sign applies for only one value of U with non-zero probability. Well, it's the same thing here. So this inequality came from the same starting point. So we can say that similar to part A, 1 over U mean value is going to be equal to 1 over the mean value of U only if there is one U value with non-zero probability. Okay, so let's call that value x. So you would have 1 over x mean value is equal to 1 over x mean value. Since there is only one value, this would give you 1 over x equals to 1 over x. So basically this conclusion is verified. Okay, so let's review what we said. We started out with this expression sum over Rs, where R and S are counting over all possible values of U, probability R, probability S, UR value to the power m, US value to the power m, parentheses squared of UR minus US, where m is any integer. When m is even, you have ur to an even power, us to an even power, ur minus us to square. PR and PS probability is a number between 0 and 1, so this is greater or equal to 0. If m is odd, then it depends on the product of ur and us. So ur and us, if they are both positive or if they are both negative, the product will be positive. So only for non-negative or all non-positive values of ur and us, this is going to be greater or equal to 0. So we started out with this expression being greater or equal to 0, and then we show that u to the power n bar squared should be less or equal to u to the n plus 1 bar, u to the n minus 1 bar, where n is n plus 1. And this was holding for m even. If n is n plus 1, that means it holds for n odd. For m odd, which means n is even, all u values should be non-positive or non-negative. And as a special case, when n is equal to 0, this inequality gives us the average value of 1 over u is greater or equal to 1 over the average value of u. Okay, so I have written this inequality, and then I have expanded the square, parentheses square, ur squared minus 2ur us plus us squared. And by distributing this, I have obtained sum over rs, pr, ps, ur to m plus 2 us to m, and terms like this. And basically I have recognized that this is just a distribution of addition over multiplication, so it has two terms. So in each term I have the average value of some function of u. So in the first one I have u to the m plus 2 average value, and in the second one u to the m average value, so on and so forth. So I realized that this basically inequality gives me the result u to the m plus 2 average value times u to the m average value is greater or equal to u to the m plus 1 average value squared. And by substituting n equals m plus 1 or m equals n minus 1, we have obtained the result suggested in the problem statement. By substituting n equals to 0 here, we have seen that u bar multiplied with 1 over u bar, 1 over u parentheses bar is greater or equal to 1. So this basically suggests the average value of 1 over u is greater or equal to 1 over the average value of u. And since n equals 0 is a special case, n is odd here, that would mean we are looking at m is even, n is even here, so we're looking at m is odd case, so that means all non-negative and non-positive u values. This will hold, and the equality will hold if the average value of 1 over u is equal to 1 over the average value of u. That's only possible if you have only one u value with non-zero probability. And here we have shown it explicitly. If that value is x, then 1 over x equals to 1 over x. But this actually comes from the starting point here, where we have looked at the expression sum over rs, pr, ps, ur to m, us to m, ur minus us squared. This is going to be 0 if ur is equal to us for all non-zero probabilities. If you have a 0 probability, it's 0 anyway. Okay, so that will be our conclusion.